Everyone, welcome. I'm just going to set up a few things and we'll get started in a minute. In the meantime, I'd like to know if anybody can hear me, if you can see me, if you can see the screen right now. Please type in chat if you can see everything and everything is working. Perfect, thank you. So let's wait until a few more people join and then we are going to get started. I think we can start right now. So once again, everyone, welcome. In today's webinar, we are going to be talking about some of the basic features of neural networks. Good morning. So we'll be discussing some of the theoretical stuff. We'll be discussing how neural networks work. We will be discussing a little bit about the math of how they work. And right away, I want to say that it's not going to be anything too complicated. We will just be going over some of the basics. And we'll also be discussing where we can actually apply these neural networks, how we can use them for any practical purposes, how we can apply them into some real job or something like that. So right away, I want to say that neural networks, they're a huge thing right now. As time goes on, they will become bigger and bigger. Right now, they can be applied to almost any sector of the economy. Pretty much any job, well, almost any job can be in some way at least augmented a little bit with neural networks. So the technology exists right now. It's just that the economy hasn't caught up yet, but as time goes on, it will catch up and AI developers will become more and more in demand. So this webinar is going to be about 2 hours long. You can grab some food, grab a drink. If you have any questions throughout the webinar, please feel free to type in chat any questions you have regarding any of the theoretical stuff or any of the organizational stuff, and I will do my best to answer you. So periodically, I will be stopping to answer any questions that might pop up in the chat. Okay, so the first 5 minutes of this webinar are going to be, we'll be talking about our organization, and then for the rest of the 2 hours or so, we'll head into the content. And with the last 5 or 10 minutes, we'll also talk a little bit about our organization. We are a commercial university, and we have almost 2,000 people that are enrolled in our courses. We primarily do two things. The first thing is that we teach people how to create neural networks. We teach people all the ins and outs of artificial intelligence, where it can be applied. So we have 15 courses just for that. And out of those 15 courses, we have 2 main courses. These courses, they start with the very fundamentals. We start going over some of the basic frameworks, the materials that we need to create neural networks. And then we start with the more basic neural networks, and then we go deeper and deeper into the topic. We cover all sorts of things like text classification, some generative models. We cover autoencoders, genetic algorithms, and then by the end, we go into the really advanced stuff. So the reason that there are 2 courses is because the first course is geared more towards the people who haven't really ever programmed in their lives. So we start with the very basic things. We start with like how to code in Python. We start with some of the libraries that we'll be using. But we also have another stream that basically covers the exact same material, but it starts further on in the course. So you don't cover any of the basics like how to program in Python. Most people will be taking the light course. Most people typically take the light course. Most of our students are people who have never programmed in their lives before. Most people come from all sorts of different backgrounds. And right away, I can say that there is no problem with that at all. Like middle schoolers take our courses and they learn how to create artificial intelligence models. And the second course we recommend for people who have programmed in their lives. It doesn't have to be any specific language, just people who have that sort of programmer's mindset. So those are our two main courses, but we have 13 other courses. And by the way, we are creating more and more courses. These courses, some of them are geared towards the more advanced users. For example, in our main course, we might have one lecture where we talk about, like, for example, text classification. And then we have a whole course that goes much, much deeper into that topic, where we cover all the ins and outs. Like in the main course, we just sort of lightly cover it on the surface, but in one specific course, we go much deeper into that specific topic. We have a whole separate course about mathematics. So right away, I want to say that there isn't going to be any super scary, super advanced math involved. Or rather, more accurately, there is going to be a lot of super difficult and scary math, but we won't have to know all of it because we are going to be using all of the frameworks that have all of this math, all of the everything that we need, all of the code sort of already made for us. And all we need to do is know how to piece these blocks of code together in a way that actually leads to good results. And that is just orders of magnitude easier than writing all of it from scratch. But we have a course that can teach you how to create neural networks from scratch. We have a separate course that teaches you how to integrate the final product into some service where it can be applied. So we have a course that deals solely with the mathematics. That is more oriented towards the very advanced users, like the senior AI developers. Those guys, they make like $300,000 a year. Like they do some really heavy lifting, but it pays off. But for the majority of users, we won't need to know that. And on the other end, we have some lighter courses. So we have courses, for example, that can gently glide you into our main course. If for some reason you're not feeling confident, for whatever reason, if you want to maybe take it more slowly, more gradually, we have courses that can teach you, for example, how to code in Python. Just the very, starting from the very basics. And the reason we are talking about Python, the reason it's a Python course is because most neural networks, pretty much all neural networks, actually I wouldn't say all, but the vast majority of them are built using Python. So all of the content in all of these courses is made by us. It's made by our AI developers. And so far we have 318 unique lectures, lessons regarding all sorts of different topics. But we are making more and more. So right now we have 318. We recommend usually takes about a week to learn a topic. So it's going to take like 5 years to learn everything that we've made so far. And by that time, we'll have made even more content. The other thing that we do is we make commercial projects. We've been involved with hundreds of commercial projects. We have a few ones that we are really proud of. So we've been contacted by all sorts of big companies, even by governments. But there are a few ones that really stand out. The first one involves an autopilot, basically like a drone, a small drone that flies through an interior of some building. And it's like an autopilot, basically. The neural network that is integrated into that drone, it can basically allow the drone to process where a window is, or it might see something like that thing over there is a door, and then it might see if that door is open or not. And if it's open, it might choose to fly through that, and it will basically plot its own course. And it's like a Tesla autopilot, but for a tiny drone that flies throughout some interior of a building. And its purpose is to collect some information. So usually when there is like some construction going on or something like that, it might fly into some interior, take a bunch of pictures everywhere, and it would process those pictures. It would see, for example, okay, that wall on the building, it hasn't been painted yet, or maybe we need to install some drywall in it. It might see some railing or a place where there's supposed to be railing, and it might classify if there is any railing installed or not. The other two big projects actually that we have, kind of a two-in-one situation, is we're making neural networks for medicine. One neural network allows us to take basically like a picture of some skin rash or something like that, and a neural network can classify the disease, can can give advice as to how to treat the disease, but its main purpose is to identify what the disease is based off a quick picture. So we hope that it can alleviate a lot of work for doctors, so that instead of going to the doctor, you could just whip out your cell phone, take a picture, and the neural network will classify what the disease is. We're working on improving this neural network. It's not quite as accurate as doctors yet, but we have another neural network that is actually more accurate than any human specialists or doctors can claim, or the vast majority at least. I'm not going to be super bold and say that no doctor in the world can do better than this, but the vast majority of doctors I don't think can do something that well. So the other neural network is where someone can give an audio description or write some text, a detailed description of their symptoms. Like they might say, oh, my chest hurts when I do this, or when I run, or when I do something physical, I start vomiting, or my back hurts, or something like that. And based on that textual or verbal description, the neural network will be able to provide, it will sort of, it's going to tell what the disease is. It's going to provide a description of the disease. It's going to tell you how to treat it. It's going to give a diagnosis. And it's accurate to about 98% of cases, which is more than what most doctors, like most professional doctors who have studied their entire lives doing this thing, can claim, which is really amazing. And we'll be seeing this a lot. A well-made neural network that was trained on a big database is actually less prone to error than human specialists are, even if those human specialists have spent their entire lives studying just that one field. The other thing that I want to quickly mention, this is a very ambitious project that we're working on. We're working on neural computer interfaces. So right now, most people, they control their computer, they type stuff, or they open up new windows, new menus, just using the standard sort of the mouse and keyboard. I can't show you my keyboard because it's part of my laptop. So just using the mouse and keyboard. But a neural network can allow a person to actually control the UI with their brain, like literally using their brain waves. Some nodes or some helmet would be hooked up to the person's forehead. Right now we have just standard nodes like hooked up to the forehead, somewhere to the head. And based on the brain signals that the neural network interprets from that, it is able to know what kind of text someone would want to type on the screen. Right now it's being used for people who have some sort of disability, like they physically can't use a keyboard. Right now they are actually able to use their brains to type in whatever they see, whatever they want onto the screen, like telepathically, basically. But we want to expand this neural network. We want to expand this whole project. We want to make it more accurate. We want to give it more functionality to be able to do anything that we basically do on a computer. But that project is right now in its beginning stages. But we really think that it will eventually change how we use computers. So the one last thing I want to mention is that we specialize exclusively in artificial intelligence. Everything that we do is going to be in some way, shape, or form related to AI. All of our courses, all of our materials. So that's it about us. Right now, we are going to head into the presentation. So once again, if you have any questions about any of the material, please feel free to type them in chat, and I will periodically be pausing to answer any questions that you might have. So right now, I'm just going to drop the contacts of our university for future reference. And right now, we're going to head into the meat of the whole webinar. So, artificial intelligence. What qualifies as artificial intelligence? Let's talk about that first. In short, artificial intelligence is anything that performs some sort of intellectual task. I'll be talking about what qualifies as an intellectual task in a minute, but right now I want to say that we have two types of artificial intelligence. The first type of artificial intelligence that we have is called general AI. This is mostly what you see in the movies. So something like Skynet, something that oftentimes you see this trope of this super advanced AI just taking everything over from humans. And this type of AI is characterized by basically being able to perform a wide variety of tasks. It's not just limited to one small specific subset of tasks, but it's able to do a lot of different things. And it doesn't have to be like a super smarter than human AI. It can be something a bit goofy, like from the Star Wars movies, like C-3PO, for example, a goofy little robot, but he can do a lot of things. He can, like, I don't know, like repair stuff, translate, cook food, a lot of different tasks. This type of AI, in practice, it doesn't exist yet. But most scientists are absolutely convinced that we will have something like that within like maybe 30 years, a few decades. But right now that doesn't exist. Right now it's only in the movies, it's in pop culture. What we have right now is called specific AI or narrow AI. This type of artificial intelligence is only good for performing one very narrow set of tasks. So for example, Tesla's autopilot. It can drive cars. It can drive cars very well. In fact, I believe it's less prone to crashes, less prone to accidents than most human drivers are per million miles. And it can react a lot quicker than humans. It can do a lot of things much, much better than most humans can. Again, I won't say all humans, but better than most humans can. But the same neural network, it won't be able to predict the weather tomorrow. It won't be able to cook food for you. We have neural networks, we have artificial intelligences that are able to do that. But an artificial intelligence that can cook food won't be able to tell you what the weather is going to be like tomorrow. And it won't be able to drive a car. So narrow AIs, they can only perform one specific set of tasks, but they can still sort of think creatively on their own within that specific set of tasks. So onto what qualifies as an intellectual task. An intellectual task is anything that cannot be solved using a hard-coded algorithm, a predefined algorithm. So for example, let's talk about what can be solved using a pre-coded, hard-coded algorithm. We have computer graphics. I imagine that a lot of people play video games. I, for one, love to play video games. Sadly, I don't have enough time recently to do that, but that's fine. When we have video games, we typically have 3D graphics, and those 3D graphics are incredibly advanced from a mathematical perspective. So if you even want to draw just a single three-dimensional cube onto the screen, that cube is going to consist of pixels. Each pixel consists of 3 different values, and most monitors have millions of different values. And some combination of those pixels is going to create any image that you see on the screen. For example, right now we have this image of the silhouette of a person. So that is made by combining pixels in some way. When you are generating 3D graphics, like right now it's just reading some image off the hard drive or off my Google Drive, somewhere off the cloud, but when you're actually generating those graphics, there is a lot of math involved in that. So generating a single 3D cube, you have to define where all of the vertices are. You're basically plastering a 3-dimensional image onto a 2-dimensional screen. You're drawing it in a way that gives it an illusion of 3 dimensions. So you want to define where all of the vertices are. You want to define where all of the sides are, how that's going to be displayed. And then that cube might be moving. It might be translating left or right. And depending on how it's translating, you would have to calculate again how much of each side you can see. So for example, if that cube moves somewhere to the right, you would see more of its left side. It might be moving up and down in the same manner. It might be getting closer or farther from the screen. Like if it's farther from, sorry, not the screen, what am I saying? The camera. So if it's farther from the camera, the cube might be smaller. If it's closer to the camera, it might be larger. It might be rotating around its own axis or around some common axis. So you will have to define some set of mathematical equations that allow it to change all of its vertices, that redraw the cube however many times a second. Then you would want to make it look nice. You would want to apply some texture onto it. You would want to apply some shader, something that is going to look at each of those pixels and it's going to perform some complicated math and it's going to change all of their colors. And that's just the example for one cube. This is the simplest problem out there. But when we play video games, like some big video games on the Unreal Engine, we have millions of these polygons generated continuously at any given moment. So you have to reapply this whole procedure millions of times over, and you want to reapply it in a way that makes it run fast. You don't want the code to run super slow, so you only have like 1 frame rate per second on your computer. You want 60 FPS. So you're going to have to optimize that algorithm. And there is an incredible amount of complexity involved in that. It's a wonder that we've learned how to do that at all. But each and every step in that algorithm is hard-coded. So that means that at some point in time, a bunch of different programmers, probably more than one programmer working on this problem, they wrote out some set of instructions, and all the computer does is look over this set of instructions step by step, and it executes that code line by line. So for example, first it might read this line of code that does it to do one thing, and then it might read the next line of code. And these combinations of instructions create the whole 3D world. There is no actual unique or creative thinking that is done by the computer in this process. It just does what we tell it to do, like every single set of instructions, it just executes it to the letter. But there are a lot of problems that can't be solved using these hard-coded algorithms. So one very simple example of such a problem is classifying between cats and dogs. We might have a picture of a cat over here, and we might have a picture of a dog over here. And we can draw cats or dogs in any way. We can draw them like in a realistic fashion. We can take realistic photos. They can be like Microsoft Paint doodles. There are all sorts of different breeds of cats. They might be like sitting in different environments, different poses, like lying down or pouncing on something. And the computer's task would be to learn how to classify, or to classify which picture represents a cat and which picture represents a dog. So if you have like some combination of pixels, you have a cat. And if you have some other combination of pixels, you have a dog. And there is basically, effectively, there is an infinite amount of possible combinations, and we have to classify for all of them. We have to give the correct answer. Like, there is a ridiculous amount of possible combinations. There is pretty much no way to solve this problem using a hard-coded algorithm. In theory, it might be possible, but in practice, I don't think anyone would manage to do this in 1,000 years, not to any reasonable degree of accuracy, but we want 100% accuracy. However, this problem is very simple to solve for an artificial intelligence. So an artificial intelligence is going to think a little bit outside the box. It's going to have to think a little bit outside of its narrow set of instructions to solve this problem. This is just one example of such a problem, but there are many more such tasks, like recognizing audio, like converting audio into text, or performing sentiment analysis, deciding if some conversation or some review that was left on some product, if it was a happy review, if the customer was satisfied or not. Predicting all sorts of things in the future, like predicting the weather. This can be done using a hard-coded algorithm, but the results you'll be getting are nowhere near as good. Driving cars, knowing where to plant crops, and a million other things. If we were to be going over all of the areas where AI can be applied to, we'd be here until the next millennium, because there are literally millions of possible areas. So this slide contains some presentations, some examples of AIs, of what they can do. So right away, I want to say that in this picture, none of these people actually exist. All of these faces were generated by a computer. If you look closely by each columns, you can kind of see that this is the same person. Like, this is the same woman, this is the same child, this is the same woman. They face the camera, the same angle, and so on. They can edit photos. So in this example, some scientists, they have the original image up in the top row, and then they redrew some of that image. They just like physically took an eraser and erased a part of that image, and then they created a doodle of something. And the neural network is able to process all of that information, and it's able to edit that whole photograph in an instant in a way that looks natural. We also have this example. This is my favorite example from NVIDIA. NVIDIA is into a lot of these generative models that generate all of these graphics. So this neural network on the left side, you can see basically an MS Paint doodle. And on the right side, once again, we have a generative model that converts this whole doodle into some realistic landscape. Or basically, it sees that this green color, it knows that it corresponds to some plants, and it draws those plants. And these rocks, this brown color corresponds to rocks. But it also knows the correlations between all of these features. So you don't get to see it here, unfortunately, but there is a video of where this is done. When this blue line here is drawn, the waterfall is drawn into the picture, but it's not just drawn into the picture, like it's not just copy pasted onto the image. All of the features around it change as well. So the rocks, for example, there is erosion wherever we have waterfalls, we have a lot of erosion. So the rocks change shape. Some shrubs start to grow around the waterfall because we have more humidity that allows more plants to grow. You might notice that there is, okay, it's kind of hard to see with this small image, but there is reflection in the water. The amazing thing is that none of these correlations were taught to the neural network at any point in time. The neural network just observed millions of examples on its own, and it came to these conclusions on its own. No programmer ever taught the neural network that water reflects stuff. The neural network sort of learned that on its own by looking at millions of examples of water and some object that is reflected above it. We have some more examples of image segmentation. So this is a very high end of example of classifying images. In this example, a neural network is able to look through an image and it's able to not just tell us what is located in the image, but it's actually able to tell us where that thing is located or if that thing is present in the image at all. So it might say, this is a truck, and it might highlight that in this greenish. It might say that this is a bicycle or this is a person, which it highlights in red, and so on. Then we have some other examples, like this example is a neural network converting a 360-degree photo that was taken on the left into a 3D model. So then we have, well, Tesla's autopilot, I think everyone knows about that. It's a very famous example. And then we have another NVIDIA example. So in this image, this part of so what you see on the left, it was what was actually filmed using a dash cam. Just as some car was driving around, it filmed all of this. And on the right side, we see the same image that is redrawn to make it look like it was taken in the summer. So all of the people would be wearing summer clothing. All of the snow, all of the ground that is covered in snow that looks white would be converted to green so that it looks like it's just grass is just growing. But all of the objects that don't change between the seasons would stay the same. Like the sky changes, but the exact cars or buildings don't change, which is really amazing. These are all examples of image generation. This is just one tiny area of where we can apply neural networks. In fact, this is just one tiny area of where we can apply just generative neural networks. We have neural networks that create music. We have neural networks that are able to write short poems or books. There is a very humorous example that you can find online of when an AI tried to write a Harry Potter book. The title is something like, I don't remember the exact title, but I think it's Harry Potter and what looked like a large pile of ash. It's a very humorous. People on YouTube made like whole animations out of it. It makes no sense because neural networks, they're not advanced to that stage yet where they can actually write a huge long text that is comprehensive and correct and resembling what a human author would write, but it's very humorous nonetheless. And you can see some examples of the neural network thinking of some creative things, but it's not quite in the right ballpark. So now let's talk about data science. Wherever we have neural networks, wherever we have machine learning, we have data science. Data science goes way, way back. So data science in general, it's when we analyze some sort of data and we draw some conclusions from it. usually we'll be analyzing some huge volume of data, and we'll be looking at all of the correlations. For example, the example that I always like to bring into this case, is we might have, for example, a correlation between crime and income. There is an actual correlation between that. And the general thesis is that the more someone's income is, the less likely they are to engage in violent crime. Because the other conclusion is that the more wealthy someone is, and I'm not quite sure about this, but I believe the other conclusion is that the more likely they are to engage in some non-violent crime. So data science is when we draw all of these conclusions by looking at a huge data set. Data science is data scientists are hugely in demand right now. It is the very most in demand profession right now. And it will be for many decades to come. Right now, we are seeing a revolution in data science. That is where we can get machines to do this. Data scientists make incredible amounts of money, and they are super in demand, and they will continue to be super in demand for like the next 30 years. After 30 years, we might have something else. Like a lot of people are saying that we will have genetic engineering or something related to biology that is going to be super high in demand. Right now, we have data science. We have two examples of data science. So the first one is sort of the traditional data science. That's when humans would look at data, like actual people would look at data, and they would draw some corresponding conclusions between all of this. So this data science has dominated for, well, forever basically. But as time went on, as computers became more and more powerful, we've come up with algorithms that can help machines do this exact same thing. And that is what we are seeing right now with machine learning, with artificial intelligence. This is where artificial intelligence really comes into play. So right now, I'm going to give an example of what a human scientist might do. For example, historically, data scientists were employed, well, they were employed by a lot of organizations. As an example, I'm going to give the example of a bank. Banks are interested in giving out loans because they know that they are going to be paid back that loan, whatever they gave out, plus some percentage on top. But oftentimes there are those people that simply can't pay back their loans, or sometimes there are those more insidious people that never have the intention of paying back the loan. But usually it's because people can't pay back the loans, and the bank isn't interested in giving these types of people their loans. So the bank wants to know who it can trust, who it can deem as creditworthy and give some big mortgage to, like some multi-million mortgage to buy a big house or something like that, and who it doesn't think is trustworthy. And it might even set like separate percentages, like how much you have to pay back and how quickly you have to pay back. So historically, a data scientist would analyze a bunch of data. Like the bank would ask a bunch of data from all of their applicants. They would ask something like their age, their history of employment, how much money they make, how long they've been employed for, what job they have. They might even ask something like how many kids they have. I don't know if banks ask this, by the way. I've never actually applied for any mortgage. So they might ask if they're married or not, a bunch of other stuff like that. And the data scientist would look at all of this data. And they might see, well, the no-brainer conclusions would be something like, okay, people who make more money, who have stable employment, who have been employed for a long time, they will be able to pay back that loan more easily. People who have a higher credit score, who have a better credit history, they are more trustworthy. But then they might also pick out some very, like the less intuitive correlations. And I'm just going to be making up these correlations, by the way, but they might see something weird, like maybe the people who have more kids are more likely to not pay back that loan, or maybe the people who are married are more likely to pay back that loan. So the purpose of the data scientist is to find all of these correlations. And ideally, the data scientist would convert all of that data into numerical format. Like they would actually create a function that takes in a bunch of parameters, like f of x, y, and z, and a million other variables equals whatever we have. They would make some equation that is going to take in all of these numbers. So something like married, yes or no, it would be converted to numerical format where 0 would mean married and 1 would mean, or 0 would mean not married and 1 would mean married. And this mathematical function is going to work with all of these numbers, and then it's going to give a single output. And that output is going to be whether or not that person is creditworthy. So a 0 would mean that, yes, they are or probably it would mean like, no, they aren't creditworthy, don't give the loan. Whereas a 1 would mean, yes, they are creditworthy, we want to give them that loan. So historically, this job was done by people for many, many decades. But then machine learning algorithms came around, and nowadays machine learning algorithms can do this same thing. So a huge portion of data science is now done by machines. A machine is going to look at that same data set and it's going to write its own equation automatically. It's going to come up with some function that takes in all of those parameters and gives some output. And that output, in our case, it would correspond to whether or not the person will be deemed creditworthy. So machine learning algorithms are able to do this much faster with much greater efficiency, not always, but oftentimes in many cases. And they can do it in, well, we don't need to actually employ people. We just have some code that runs on our computer. So that is where machine learning comes into play. Machine learning is when machines analyze all of this data. So machine learning has actually been with us. It's been around with us for a while. It's been around with us since probably like the 1950s, maybe even earlier. So we've had all of these algorithms for a while, but historically speaking, computers simply weren't powerful enough and these algorithms weren't advanced enough. So during like the 1950s, 1960s, 70s, 80s, humans still did the majority of the heavy lifting. Then we got a bunch of classical machine learning algorithms. So we got something like support vector machines, KNN algorithms, or random forests, stuff like that. There are dozens of these algorithms, by the way. So these algorithms, they slowly started to take over the work, what the actual employees do, what actual humans did. They started to take more and more of the work. They started to take it over. But then we also have neural networks. Neural networks are another type of machine learning algorithm. Neural networks have actually been with us since the 1950s. So some biologists made basically a portrayal of how they think the brain works, and mathematicians converted that into digital format, and that's how we got neural networks. Neural networks were, historically speaking, they were very weak. Very rarely would they match the performance of the classical machine learning algorithms. But as time went on, as CPUs became more and more powerful, as computers, we had access to more and more computer resources, computational resources, neural networks started becoming more and more powerful as well. So in the year 1995, we would see quite a bit of work being already done by our classical machine learning algorithms. But within, like, if this was to be the whole field of data science, we would see a respectable portion of that being done by classical algorithms. And within that, we would have like a tiny, tiny little nugget that neural networks are responsible for. But nowadays, neural networks have basically taken over. Neural networks are able to perform much better than classical machine learning algorithms for the vast majority of tasks. Sometimes, like, I would say even less than 5% of cases, we might see an example of where a classical machine learning algorithm might give us better results than neural networks. But generally speaking, like 95% of the time, neural networks will win over. And the reason for that is because we have so much more, like so many more computational resources available to us now. CPUs are so much faster. We've been able to learn how to use GPUs to run all of this code. So neural networks, they are very resource intensive. We'll be talking more about that a little bit later. But neural networks, basically, their distinguishing feature is that they can provide very, very good results, but in doing so, they will eat up a ridiculous amount of computational resources. Like even nowadays, we barely have enough computational resources. In fact, we can't use CPUs to run neural networks. Like we can, but it's going to take a ridiculously long time. We'll be using GPUs to do that, and even that isn't going to be fast enough. So we then have two different subsets within machine learning. So we have data science, and within data science, we have part of it which is done by humans and part of it which is done by machines. Within that, we have part of that which is done by classical machine learning algorithms, and we have something that is done by neural networks. Then we also have different tasks within machine learning. So we have simple tasks. Simple tasks, some examples of them might be something like classifying between cats and dogs. Or something like a very simple example might be analyzing texts and predicting which author wrote each text, judging by how many times each specific word was used, or something like that. But then we also have deep neural networks. Deep neural networks are able to give us very good results. They can perform, in fact, they can perform tasks which classical machine algorithms can't perform at all. For simple tasks, neural networks win over classical algorithms the majority of the time, but not 100% of the time. But deep learning can't be performed by classical ML algorithms at all. So examples of deep learning might be the generative models that we saw. There is another interesting website, something like thispersondoesn'texist.com, where the website can just generate the picture of a human face for you, just right on the fly. So anything that has to do with generative models, an AI creating music, writing texts, or image segmentation, which is when the neural network looks at some image and it sees like the whole image and it sees that, okay, this corner might contain something like a dog and this corner might contain a car and this whole image might be a tree. So that is what image segmentation does. Then we have another example of where instead of outlining this in bounding boxes, a neural network can actually color in that pixel by pixel, which by the way, we'll be looking at in the demonstration later on. So deep neural networks are really taking over. The correlation of how many deep neural network tasks we have to the classical simple tasks is also growing. So again, if anyone has any questions regarding any of the material, I'd be more than happy to answer them. Right now, we are going to look at some disadvantages of neural networks. So we've talked about how they're so wonderful, how they can do so many things. They have some advantages, some big advantages, and they have some disadvantages. So the first advantage is that neural networks learn on their own. All they need is a data set. A programmer doesn't explicitly tell a neural network any of these correlations. So for example, at no point will a programmer be telling the neural network, okay, if you see this, that is the exact result. A neural network is going to learn all of this by its own. And it's going to do that using a database. So that's a downside. We need a huge database to train the neural network on. Oftentimes, I like to give an analogy with a human in this case. When we create a neural network, we can think of it as just a newborn human, just a human baby that was just born. And let's pretend for a second that we can converse with this newborn baby. We can exchange ideas with it. We can communicate with this child. Like we can give it concise instructions that we would be able to give to adults. If you show this baby a picture of some trees and ask like, okay, Billy, show me which one is an oak tree and which one is a pine tree. Well, the child would just like look at you like you're crazy. Like he would probably say like, I was just born. Why do you want me to classify all of these trees? How can I know all of this stuff? Neural networks are pretty much the exact same in this regard. So they don't know anything when they're quote unquote born. But as they see examples of, in our example, pine trees and oak trees or any other kind of tree, they would learn over time by looking at all of these examples. They might see, okay, pine trees have these needles, so whenever I see needles, that's a pine tree. Or a birch tree has like a lighter color, and so on. Neural networks work in the exact same fashion. They require a database that they are going to look at and they are going to learn from. They are going to look through that database and they are going to look at all those examples and they are going to learn from that. But unlike with a human child, like a human might be okay with seeing like 5-10 examples of all of the different types of trees. Neural networks will need thousands, tens of thousands. The more the better, really. But thousands is a very small data set if we're talking about images. So we are going to need to collect this database somewhere, and that is going to take time and money. Okay, have we a question right now? What is the scariest hypothetical of a neural network gone wrong? Well, that depends what you define as scary. I guess, well, one thing that I could really see happening is neural networks, they're prone to error, but they're less prone to error than humans are. But sometimes they still make silly mistakes. Like there was a few years back, there was an example of a Tesla autopilot, which was still able to do like crazy maneuvers that human drivers couldn't be able to. It did some very silly mistakes. It made some ridiculously silly mistakes. Like it couldn't see a big fence that was right in front of it. I'm sure that's been patched by now, but that can happen. So I would say the scariest hypothetical example of a neural network gone wrong would be when a neural network is responsible for something really, really big, like controlling all the nukes or something like that, deciding when to launch missiles, and then it makes like a stupid example, like it makes a stupid conclusion, like something like what the Tesla autopilot did in this example. But that's just my opinion. Some people might say that Skynet might take over. I don't know if that's going to happen. But when we really assign these complicated tasks to neural networks, we need to be a little bit careful. So this actually drives right into the next point. When we make neural networks, we don't need expertise. We don't need like to be super high quality experts in that exact field that we're making a neural network for. So right now, our university is making a bunch of neural networks that are used for all sorts of medical purposes. However, our AI developers, they're not like, they don't have medical degrees and they don't need to. And this applies to a lot of fields. We don't need to be experts in the specific field which we're making neural networks for. That's because the neural network is going to look at some data and it's going to learn on its own. It's going to arrive at all of the necessary conclusions on its own. So it's still highly recommended to be an expert, or I wouldn't say highly recommended, but it would still be highly beneficial to be an expert in some given field that you're making a neural network for. But oftentimes we can just consult the actual experts. Like all we need to know is our code, our programs, our computers, and then we would talk to some professionals in the field. We would ask them, okay, if we're performing this exact task, what are we looking for? Like if we're looking at defects in metals, what are some indications that might like indicate those defects? What are we going to be looking for? How are we going to create our database? And sometimes these people can even give us a database. Sometimes we are going to need to collect the database on our own. So we'll be discussing about that a little bit more, but collecting a database, it takes a long time and basically it's painful. Sometimes we don't need to collect a database on our own. Sometimes we can use data that we already have somewhere. So the other positive from that is that a lot of the times neural networks, they are less prone to error than humans. If it's a well-made neural network that's been trained on a large, varied data set, a high-quality data set, it will often arrive at better conclusions, or it will be able to give better predictions than human experts who have spent their whole lives studying in this specific field have. So one example that we had from one of our graduates in our university, they have a thesis project at the end of the course. And right away, I want to say that no one fails the thesis project because we help all of the people as much as necessary. We provide all the necessary help for that thesis project. But we had one student that made a thesis project that would analyze some minerals, some rocks or something like that, or some metal, I think it was metal, and it would try to find defects in that metal. Like maybe there are microfractures, or maybe it's too malleable or too brittle or something like that. The neural network that was trained for this purpose was accurate to within about 97, 98% of cases. Human experts were only right about like 80, 85% of the time. So this is just one example. We also see a lot of this in medicine and in many other fields. We have cases where neural networks do things that humans can't do like at all, as we saw in the example of converting a 360-degree image to like a 3D representation. That is the case for well-trained neural networks that were trained on a high-quality data set. So there are some downsides, however. The first, as we've discussed, we need databases to train on. Databases take a lot of time to collect. They take a lot of resources to collect. We will be hiring, oftentimes like big companies hire actual people or even actual departments for this purpose. Then the next downside is that they require a ridiculous amount of processing power. The more processing power we have, the better. Like I can't give an exact estimation, an exact number as to how much processing power it takes, but as we've had more and more processing power, we've gotten better and better results. Right now, we can't even run neural networks on CPUs. We have GPUs that we are using just for this purpose. So neural networks, as it turns out, a lot of the math involved there is just a bunch of matrix operations, and GPUs are perfect for that. GPUs are able to give us results about 50 to 100 times faster than CPUs. They're able to train neural networks 50 to 100 times faster than CPUs. Obviously, it depends on the GPU and the CPU in question. That's just a rough estimate. So even then, it might take weeks, months, probably no longer than months. At the very highest end, it might take months to train a very big, complicated neural network using a huge data set for some very big project, like a big company might be doing this using a supercomputer. Or for the basic neural networks that we'll be looking at in our main course, even those will typically take a couple of hours to train. And by the way, we won't have any hardware requirements for that because we'll be using computational resources in the cloud. And the last downside is that neural networks are a black box. So neural networks, going back to the example with the mortgages, they would basically create a long equation on their own. They would create just some ridiculously long, complicated equation, similar to what the data scientist would, that's going to read in all of the inputs and give some final result as the output. The human scientist, the data scientist might say something, okay, let's take a look at the average income, divide that by the number of days the person has worked multiplied by something like how many years they've been employed for. And they would be able to give some sort of intuitive explanation as to why we'd be looking at these features. The neural network isn't going to be able to do that. It's just going to create this ridiculously long equation, but it's not going to explain why it is the way it is. A neural network's logic is very removed from what humans typically think of. So it's just going to come up with some weird equation and it's just going to work. We don't know why it works, but we'll be able to see in practice that, okay, this exact combination of all of these numbers, yes, that works. That gives us good results. So they're a black box. They'll take in some input, they parse that data, and they give some output without explaining why that is, why the answer is the way it is. So this is only really going to be a problem for some specific topics. For example, something like court cases. We are 100%, I'm sure that we can use neural networks in a lot of cases, like regarding all sorts of legal disputes, all of that stuff. But even determining like if someone is guilty or not, there is a whole science called socionics that basically says that you can determine some qualities of the person, their personality, just by looking at their physical appearance and specifically at their face. So I am sure that a neural network will be able to determine who is guilty and who isn't guilty, like if the accused is guilty of some crime just by looking at their face. Probably not 100% accuracy, but still to some accuracy that is well above just random accuracy, just randomly guessing. However, even if we ignore the fact that this isn't going to lead us to 100% accurate results, no court will ever accept a result that just involves a neural network looking at two pictures of two people's faces and just saying, guilty, 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 50 years in jail, death sentence. That's never going to happen because we need to actually explain how we know that that person is guilty. We have to have some sort of probable cause. So another field is science, all sort of scientific work. When Albert Einstein wrote the equation E equals mc squared, so this equation was actually based off of intuition. Albert Einstein, well, he derived it mathematically, but he derived it using intuitive examples. Like he gave examples, okay, imagine that we have this hypothetical case, and then this happens, and then that happens. So let's represent that all in math and all of that. And that eventually leads to E equals mc squared. This algorithm can be, like this equation can be verified, it can be derived in a huge number of ways. But a neural network, even if it can derive some equation like that, or it can like tell us some correlation, the scientific community isn't going to accept an answer like the neural network came up with this equation. Just trust me, guys, it works. They're not going to accept that because each step in that equation needs to be derived. We need to explain how the conclusion was reached. And we probably have a few other cases along those lines. What are neural networks in layman terms? That's a very good question. So an artificial intelligence is something that can perform some sort of intellectual task. It can think a little bit outside of its narrow set of instructions. It can basically perform some thinking that isn't hard-coded. It can do some of its own, a little bit of its own creative thinking to come up with an answer for any given specific problem. A neural network is one method in which we can create that artificial intelligence. A neural network is the best way, in fact, in which we can create that artificial intelligence. It's not the only way, but nowadays, the vast majority of AIs run off of neural networks, and neural networks just give us much better results. So right now, neural networks dominate. You could say that it's like one analogy that I often see being used here is that it's sort of like the engine for the AI. Like if an AI is a car, then the neural network is the engine that that car runs off of. I hope that answered your question. So far we've talked a lot about how neural networks, how they're so amazing, how they can analyze all of this data on their own. Well, if neural networks were so smart that they would be able to automate this whole process from start to finish, we wouldn't have jobs. So let's talk a little bit about what an AI developer actually does in this context. So whenever some team or some company or even some freelancer gets towards creating a neural network, the first thing that we need to do is to have a database. There needs to be data that the neural network is going to learn from. And collecting that database, someone has to actually go out there and collect it. So in big companies, there might actually be a whole department of like 50, 100 people just working towards creating some big database. And the final results of the neural network will depend greatly upon the quality of the data set. So sometimes we can have some clever solutions to creating the data set. Sometimes we might have just some pictures taken using some drone or something like that, and that's going to create a data set very quickly. Sometimes we can just scrape the web, scrape the internet, read a bunch of catalogs from online stores and use that as our database. But a lot of the time, someone is going to actually have to go out there and spend weeks, months collecting this database. For example, if we want to classify trees, different types of trees, we might want to take a bunch of pictures of all of these different types of trees. And depending on the scale of the project, well, either way, if someone is actually going out there, this would take a long time. Thousands, tens of thousands of dollars per person would have to be paid. And you can imagine what happens if we have hundreds of people. So this is typically going to be done by some other people. And unless it's some freelancer that's doing everything by themselves, the majority of the time, the people that collect the database, they're different from the people that actually create the architecture for the neural network and create all of the code and train it. So on to creating the architecture. Neural networks consist of neurons. They're neurons that are connected to some other neurons in all sorts of different ways. And architecture is how these neurons are arranged. We can have different types of neurons. They can be connected to some other neurons in some specific fashion. So that is what an architecture is. Neural networks are really amazing because they resemble something like scientific work much more closely than a lot of other programming like web development or game design. We usually have some hypothesis that we think, okay, maybe this specific architecture is going to give us good results, and we would try that out. And there is going to be a lot of trial and error involved in this step, by the way. So for example, we might see that, okay, we tried out this specific architecture, this specific algorithm, but it didn't give us very good results. So then we'd want to try out another architecture. And we'd be doing this many, many times until we have something that we would decide is some results that we would decide are good results. So we would try to observe the accuracy. We would observe how well the neural network performs. And the neural network, it's going to give us two different parameters. It's going to give us a parameter as to how well it performs on the data that it's already seen before. And it's going to give us a parameter that says how well it performs on data that it's never seen before. So you can think of this as a student that is studying for a math exam. And when we study for any kind of exams, really, we go over practice problems, right? We look at how we solve this problem, and then we look at how we solve the next problem, and so on. And the hope is that, well, a student, by solving many different problems, is going to learn how to solve a general problem of the same type. Same thing with neural networks. The hope is that the neural network will be able to generalize and that it will learn how to solve any such problem in general. But a lot of times, neural networks do what is called overfitting. So overfitting is when the neural network has basically memorized all of the answers for all of the problems that it's seen before, but it's not able to generalize that to new problems. So in the context of a student, you can think of this as a student studying for a math exam, seeing a problem in the practice exam that 7 times 5 equals 35. But when it comes time for the real exam, or for some problem in real life where they have to know what 7 times 6 is, they wouldn't know the answer. So we want to make sure that that doesn't happen. There are a lot of ways that we go over in great detail in the main course as to how we can sort of combat overfitting, how we can avoid that. There are a lot of different methods. And as AI developers, our task is to make sure that this doesn't happen. Then after we've run a series of tests, after we've decided that the neural network, it's learned all that we wanted to learn, all that we needed to learn, and that it's working excellent now. We are just going to have a single file somewhere on our hard drive or somewhere on our computer. So it's just going to be like somewhere maybe on the cloud. This is just going to be a file that contains the equation that, going back to the analogy with the data scientist, the neural network is effectively going to create some very, very long equation that it's going to perform for every given problem, and that equation is going to give us the answer. So this file is going to create, contain that equation. This equation is going to be like thousands of lines long, potentially. It's going to be some ridiculously complicated, difficult equation that the computer generated. And our task is going to be to integrate this into some real purpose. So whenever we create neural networks, we typically want them to be used somewhere. A lot of farms, for example, might use neural networks for deciding something like if some animal, like some herd animal, is sick or not, just by looking at its blood sample. Or if it's more susceptible to diseases, sometimes they might want to cull the animals that are more susceptible to diseases so that the whole herd doesn't get infected. Or they might look at plants and decide if the plants are sick or if they're healthy. And we would want to integrate that neural network into either like a drone or some camera or maybe even a phone. We would want to integrate it into some service that actually lets it be used. If we have a self-driving car, we would want to integrate that into that self-driving car. So it's not just going to be doomed to an eternity of sitting around as some file on some forgotten hard drive. So far we've talked about how neural networks, like where we can use them. We've talked about what our work consists of, how we can go about making them. Let's talk a little bit about how they actually work. So we're going to delve into a little bit of the math, nothing too complicated. We'll be mostly sticking to the intuitive level. Neural networks consist of neurons. Back in the 1950s, biologists, they made a hypothesis. They said that our brain has all of these neurons that are connected to all of these other neurons. And I don't know what exactly was wrong with their model, but we know nowadays that that model isn't really correct. Their model that the biologists came up with back in the 1950s, it was close to what we have, but not really. There are a lot more things. So we know that they're wrong. The hypothesis that they came up with in the 1950s was wrong. But before we discovered that, a bunch of mathematicians took this biological model and they created a sort of a digital representation of it. And that's where neural networks come from. Neural networks consist of neurons, and each neuron basically classifies either the truth or the falsehood of some statements. It classifies the truth of some statements. So for example, our brains are made up of neurons. Whenever you touch something that is cold, like ice, there is a neuron in your brain that's activating, that's responsible for the feeling of cold. Or whenever you, for example, I don't know, whenever you feel pain, like you cut yourself, you got a paper cut or something like that, there is a neuron that's being activated that is responsible for the feeling of pain or discomfort or something like that. If you're happy for whatever reason, there is a neuron that is responsible for the feeling of being happy being activated. So this is a gross oversimplification. Like I'm going to state right away that this is a gross oversimplification, because in the human brain, and even to some extent in neural networks, these things are actually classified by clusters of millions of neurons that work together in some complicated fashion. But that is the sort of the general idea. Each neuron classifies if something exists or not. For example, if we're classifying cats and dogs, we might have a neuron that looks at the nose of the animal. And it tries to classify if it might try to classify if there is a nose. It might try to classify if the nose resembles more of a cat's nose than a dog's nose. Or it might look at a tail and try to classify if it resembles more of a cat's tail or a dog's tail. and a lot of other things like that. So each neuron is responsible for giving the truth of one specific statement or one specific condition. If that thing doesn't exist, the neuron's output might be 0. So neurons, they take in data from other neurons and they feed data into other neurons. Basically, you can think of all of these neurons as having numbers. And there is going to be a mathematical equation that determines how they pass that data on to other neurons. If a neuron's output is 0, that means that we don't see that feature. Or if it's 1, then it means that we see that feature. So neurons can also classify as to how, they can give us an analysis as to how true a statement is. For example, we might have a question like, is the animal bigger than, does it weigh more than 5 kilograms? If the weight is something like 6 kilograms, the output of the neuron might be something like 0.1. That means that, yes, the weight is more than 5 kilograms, but just barely. Or if the weight is 100 kilograms, we might have a loud, resounding 1. It doesn't have to be between 0 and 1, by the way. Neurons can take basically any value. We'll be talking about which values they can take a little bit later. So 1 in this context would mean that, yes, the weight is a lot more than 5 kilograms. That condition is definitely being met. So we have what is called, in the basic context, we have a fully connected neural network. This is a basic model of a neural network where each neuron in the previous layer is connected to every neuron in the succeeding layer. So each neuron in any given layer, okay, so these are layers, these columns, these are what we call layers. And each neuron in any of these layers takes in data from all of the neurons in the previous layer, and it feeds data into all of the neurons in the next layer. And in this fashion, some numbers, these neurons will all have some numbers, they will propagate through the whole neural network and they will give us some numerical data in the final answer. So, okay, we have a question. How long is this lesson? Will it be recorded? I believe it will be recorded. It's 2 hours long. We've went through 1 hour already, so we have like, I think 50 minutes more left to go. So I'm not, yes, I think it is recorded, but I'm not 100% sure. I'm not the one that's responsible for that stuff. So in an example with, let's give a very basic example. Let's say that we are trying to classify some animal like a cat or a dog based on 3 parameters. Instead of looking at each of the pixels, we will now look at these parameters: the weight of the animal, the height of the animal, and its length. The neural network is going to accept these inputs. It's going to pass them into these 3 neurons, and these are going to be its values. So it might have a weight of 5 kilograms, it might have a height of, I don't know, 20 centimeters, a length of 40 centimeters. And then we have the outputs of these neurons. So these first neurons are going to be asking like some very basic things. Essentially, their output, or like these neurons, they'd be asking effectively something like, is the weight of the animal more than 5 kilograms? Is the height more than 20 kilograms? What am I saying, height more than 20 kilograms? Is the height more than 20 centimeters? Then this next layer of neurons might be asking some questions. All of these neurons might be asking some more complicated questions. Like they might be asking something like this neuron might be asking, is the weight more than the length times the height of the animal? Or is the length more than double the height, or something like that? And this layer of neurons would be asking for even more complicated combinations. And it would be asking for, by now it would go onto like really, really complicated questions that have really no basis in human logic. So each successive layer of neurons, each neuron in each successive layer effectively asks more and more of these intricate questions. And then we have this final layer where we have 2 neurons. This is the neuron that has the value of the cat, and this is the neuron that has the value of the dog. So numbers will propagate through this whole neural network, and we will get 2 answers. We might get something like a 1 here and a 0 here. This means that the neural network doesn't think that whatever the inputs we gave it, it doesn't correspond to a dog at all. It thinks that it definitely corresponds to a cat. We might have an answer like this. This means that the neural network thinks that these inputs correspond to a dog, but it's not sure. It might be a cat, but it thinks it's more closely, a bit closer to a dog. And it's going to guess that this animal is a dog. Where to see the recording again later? I believe it should be on YouTube. I'm going to actually ask about that as well. I'm going to clarify that question with the people who are responsible for that. Yeah, thank you for asking that, by the way, because that's a really good question. That's something that I think I should know as well for future reference. So that's how numbers will propagate through this whole neural network, and we'll get some final answer. Any neuron, so we have neurons, and we also have these connecting weights. Let's talk a little bit about how they propagate through this neural network right now. So these lines that you see connecting these neurons, they are what we call weights. If we were to have, just for example, a weight of 1 and a height of 2 and a length of 3, I'm just making up numbers. They can be in any units, doesn't have to be centimeters or inches or pounds. We would have these weights that would also have values. So the value of this weight might be something like 0.5. The value of this weight might be 0.1, and the value of this weight that connects these two neurons might be 0. So the value of this neuron is going to be the weighted sum of all of these numbers. So 1, like this number, times its connecting weight times 0.5 plus 2 times 0.1, which is 0.7, plus 3 times 0, which is 0.7. That's going to be the value of this neuron. And then it's going to pass that value multiplied by some other number into this neuron and into this neuron and into that neuron. So each neuron is going to contain the weighted sum. There are also going to be biases, which instead of just multiplying by some number, they just add another number. Like we might have 0.7 plus 0.5. That's just going to be, the 0.5 is just a static number. Where we might have a negative number that we are going to add to subtract. We might be multiplying this by negative numbers. And we also have activation functions that decide how these numbers, like it performs some operation on the number, like it might square that number or something like that. So we have another question. Oh, no, it's not a question. So that's how numbers will propagate through a neural network. And eventually we are going to get some final result that we are going to map to some physical answer. If we had 3 animals that we were trying to classify, for example, a cat or a dog or a beaver, we might have a 3rd neuron in the final layer, where this is going to be the value of the beaver, how much the neural network thinks that the answer corresponds to a beaver. So far we've talked about how neural networks, how the actual like math functions inside them, how they give the answers. Now let's talk about how they learn. When we initialize a neural network, all of these weights, they are just going to be random numbers. And that's not going to give us any good results. The results that are spewed out by the neural network in the beginning are just going to be complete garbage. It's going to be essentially guessing. And those guesses will make absolutely no sense. But then we are going to show this neural network a bunch of data, and we are going to say, okay, neural network, learn from this data. So in our very simple example, by the way, this is a very simple example where we only have like 3 parameters and 20 neurons. In practice, we will have millions of neurons and we will have dozens and dozens of layers. So I want to get that out of the way. But the neural network is going to look at this data and it's going to try to predict some answer. For example, it might look at these 3 numbers, and it would perform that, all of that math on them. And it might say that, okay, this animal is a cat. And then it's, or actually, let's say that it's going to say that this animal is a dog. And then it's going to see, no, this animal is not a dog. It's actually a cat. I was wrong. I gave the wrong answer. And that's when it's going to perform a very complicated algorithm that's basically going to restructure all of its weights. All of these, it's going to restructure all of these little lines in such a fashion that whenever the neural network acquires, whenever it sees that same data, it's going to give something that is closer to the real answer. It's going to be more likely to say that this isn't a dog, but that it's actually a cat. And it's going to do that for all 20,000 examples. When it sees this data, for example, it might then move on to the next data point. It might see that this corresponds, it would guess that this corresponds to a dog, and it would see that, okay, yes, now it actually does correspond to a dog. So now I gave the right answer, and it's not going to change any of its weights at all. That's when the neural network will say just that it's going to just continue analyzing more examples. But whenever it sees some example that it gives the wrong answer to, it's going to restructure all of its weights in such a way that it would be more likely to give the correct answer next time. And the hope is that if it does this for many, many examples, 20,000 is like a small data set, like a small medium-sized data set, by the way, it's going to learn how to generalize. That's not a given, but that's the hope. So it's going to learn how to generalize, and it's going to be able to apply that same knowledge that it's learned onto new data. It's going to go over 20,000 examples many, many times. So we have something that is called an epoch. An epoch is when the neural network looks at the first, so it looks at all of the examples for the first time, and then it tries to solve them again. And so it's going to be looking at 20,000 examples many, many times. And then it's going to, we're going to see if it's actually learned anything. So this is the responsibility of the test dataset. The test dataset is a little smaller than the trained dataset. Its purpose is to show new examples of data that the neural network has never seen before. And we would be asking the same question. We would be asking the neural network, okay, we say that these are the parameters. Please predict this animal for me. Is it a cat or a dog? And we're going to see how many times the neural network predicts the correct answer. So this is going to, the test data set is kind of like the final exam. It's going to let us know if the neural network has actually learned how to generalize the data, how to solve the problem as a whole, or if it's just remembered all of these questions. And the hope is that it will learn how to generalize. Once again, that's not a given. Typically, it's going to do better on the examples that it's seen before, but the hope is that it's also going to do well on the examples that it hasn't seen before. Okay, we have a few questions. How much does this degree cost? We will be going over all of that at the end of the lecture. We will be going over all of that specifically. So now let's talk about, well, adjusting weights. The whole learning process, when a neural network learns, when it sees that one of these predictions that it's made was incorrect, it's only going to restructure the weights. We are going to define the architecture of the neural network. So we are going to define which neurons we have in which places, how they feed data into one another, what sorts of activation functions we have. Activation functions are just basically, they just take the value of a neuron and do something with it. Like they might square it or put it between a certain range or something like that. The neural network, all it's doing when it's learning is it's just adjusting all of these weights. So all of the other parameters are defined by the developer, but the neural network is going to try to pick the best combination of weights so that it can solve the problem. And that's the whole learning process. It's just going to be slightly adjusting all of these weights. So to recap, we have an architecture of the neural network that we define that is going to be like, we will tell the neural network, we will place these neurons, some set of neurons in some place that are going to feed into some other neurons. And then we have weights connecting all of these neurons. So we have all of these weights connecting all of these neurons. And these weights are going to change in the learning process. Let's take a look at how they're going to change. So this is a problem that is called, this is an algorithm that is called gradient descent. A neural network is going to, okay, so we have one parameter that is going to be responsible for the error of the neural network. It's often called the loss. The loss is basically a numerical measurement as to how wrong the neural network is. So for example, when we're trying to, just hypothetically speaking, if we were to try to predict the stocks tomorrow, like the stock market, if we were only off by 1 point, that wouldn't be as bad as being off by 5,000 points. So the actual degree of error as to how wrong the neural network's results are is going to be defined by the loss function or the error value. So we can define this loss to be anything that we want. We might say that it might be, in the case of like stocks, we might say that it's the how off we were squared. So if we were off by 1 point, 1 squared is still 1. But if we were off by 1,000 points, 1,000 squared is 1,000,000. So we are way, way more wrong than just by being 1 point off. We might say it's the square root of that for some other topic. We might say that it's exactly that number, like linearly. If we are off by 1 point, the error is 1. If we are off by 1,000 points, the error is 1,000. It doesn't matter too much how we define it, or actually rather it does for different topics. But the purpose of gradient descent is to reduce this error. So whenever the neural network sees that it got some wrong answer, it's going to calculate this error value. So if we have only one weight in our neural network, we would have a graph that looks like this. This is a ridiculously oversimplified example. When we have 1,000,000 weights in a neural network, which by the way is still a very basic neural network, this would be a 1,000,000-dimensional graph. So this is, to be able to show this in 2 dimensions, I'm going to be using a very oversimplified example. The neural network is basically going to reorganize all of its weights. It's going to change all of the values of all of its weights. It might look at this one weight and say, okay, let's increase its value by 0.01. And then it's going to perform the same calculations, and it's going to see that it was off again, but it's off by less. It was closer to the correct answer. So that's where the error decreased. This is going to be controlled by the gradient descent algorithm. The gradient descent algorithm is going to dictate how much we change each of the weights by. But basically, it's going to change all of the weights in the whole neural network in such a fashion that the error decreases. Like, once again, this is an oversimplification. In reality, this graph would have 1,000,000 dimensions. But no matter how many dimensions it has, we would always know where we're located, and we would know which direction we need to go in to reduce the value of the error. So you can basically think of this as climbing down a mountain. We would see that we need to go in this direction to reach the lower point. So we would go in this direction. We would keep changing weights. And each time we're changing weights, we are basically going further and further down the mountain until we would want to ideally reach, well, in theory, we would want to reach the global minimum of this graph. But in practice, we'd be happy with a local minimum, because this global minimum is typically when the neural network overfits and it gives us garbage results. So we want to go here. So there are a few things we need to be careful of here. If we start taking steps that are way too big, we would just catapult all the way onto the other side of the mountain, like onto another mountain. And then from here, we would see that we need to now go in this direction to reduce the error value, and then we would catapult back, and then we would keep jumping back and forth, and that's not going to give us any good results. But if we take steps that are too small, well, the first thing that's going to happen is that the computer will tell us, why do you hate me? Because all of these steps take a lot of computational power, and they take the same amount of computational power, whether they're big or large steps. So it's going to take a lot more processing power. But another problem that we can run into is that we can keep taking these tiny, tiny steps, but then we'll eventually go somewhere here. And here we'll once again need to go in this direction to reduce the error value. So we'll keep jumping back and forth. Once we jump back here, we'll see that we need to go in this direction. And we'll be essentially stuck in this infinite loop and we'll never get any good results. So if we were to define a step size that is just right, we would be able to navigate all of these local minimums. We would be able to pass through all of them until we reach some local minimum where we're happy. And here it can bounce back and forth. We don't really care. This is where we want to go. So in practice, we have several of these local minima, and we want to choose one that is reasonably small. So the gradient descent algorithm is going to get us there automatically. There is a lot of math involved here. But we don't need to know all of this. This is just sort of an intuitive explanation, because all of the math, when we're working with this in practice, is going to be defined by all of the libraries that we're using. So also one more thing I want to mention is that in practice, we have optimizers which can change this step size so that it's not going to be static. If it sees that we're taking steps that are way too big, it's going to eventually start taking smaller and smaller steps. And if we're stuck in like some local small valley, we're going to start taking larger steps until we can navigate through that valley. Again, there's a lot of math involved in that algorithm and we don't need to know all of that. Okay, with that, let's show an actual demonstration of all of these neural networks. And if you have any questions, by the way, while I'm loading all of this up, I would be more than happy to answer them regarding anything. So I know that especially regarding the theory, a lot of people have questions at this stage. So if you have any, I'd be more than happy to answer them. This is Google Colaboratory. This is where we will be writing our code in our main course. Google Colaboratory gives us a free GPU to play around with, and it's actually a pretty high quality GPU. Like buying this GPU on the market would cost a few $1,000s, or like $1,000 maybe. And besides, it's just a very convenient coding environment. So we can type in all of the Python code that we have here, and that code is going to be uploaded to Google servers, and Google is going to run that code. So you don't need like an advanced computer to run this. I'm running this on my laptop right now, and it's working just perfectly. So in our first example, we have an image classification problem. This is going to take a while to load. So if you have any questions right now, I would be more than happy to answer them. So right now we're loading something like 25,000 real images of cats and dogs. By the way, these are libraries that our university made. Like these are our own custom libraries. And in practice, the code is a little bit more complicated, but not really. It's still very simple. Like the amazing thing is that we really don't need to be like super good programmers to, or know a lot of math to do all of this. 15 years ago, we did, but nowadays, only the really advanced AI developers, like the seniors that make ridiculous amounts of money, would really need to know all of the tiny ins and outs. Which software would you recommend to work with music neural networks? All neural networks that we are making are going to be, well, we're going to be running all neural networks in Python for coding and training. We have two big libraries. By the way, thank you for asking this question, because that brings me to one other thing I forgot to mention. Two big libraries that we work with and that like 50–60% of all commercial projects work with are TensorFlow and Keras. They have the simplest code. There are a lot of other libraries that are a little bit more complicated from the perspective of code, but it's not like Keras is the easiest. So any project that you have, we recommend Keras. Most people use Keras. Is it needed to know basic computer science, Python, etc.? It's needed to know, you need to know basic Python, which we are going to go over in our main course. Basic computer science, no. Java, no. If you happen to know Java, that is great. That means like you have the programmer's mindset that you can jump a little further into the course, you can skip the basics. But so no, you don't need to know basic computer science. You don't need to know Java. Python, you need to know a little bit of Python. Nothing too complicated, just sort of like the basics, maybe a little bit of the intermediate stuff, but we will teach you that. No coming from non-computer science, no programming at all. No problem. The vast majority of our students are like that. So it's taken this long to load 25,000 images. This is what our images look like. Like these are images, cats and dogs. We might have like a human in the background. And the neural network is just going to classify whether or not the given image contains a cat or a dog. So let's train this model. Training is going to take quite some time. Right now, it's not going to take too long because we're using a basic neural network. But in practice, it's going to take a lot longer than this. We're going to have two parameters. The accuracy on our train set. So that's the accuracy on the data that the neural network has already seen before. And then we have a test set. So that's the data that the neural network has never seen before. And it's very common for the accuracy on the train data to like skyrocket and get really close to 100%. Even with like weak neural networks, it will get very close to 100%. But for the test set, this is the only number we really care about at the end because it gives us an understanding of how well the neural network is going to perform in real life. We are going to get poorer results in general. We aren't going to get 100%. Well, we can get 100%, but it's going to be much harder. So all we care about really is the test set accuracy. And so each of these are epochs. One epoch is one case of the neural network going through 20,000 training examples and studying through all of them. And we have a graph here that shows us how accurate the neural network was in each epoch. When we just start training the neural network, like it's absolute trash. It doesn't know heads from tails. 50-50 is it's just guessing. If you say that every picture contains a dog, you're going to get 50% accuracy. But then as we keep training it more and more, the accuracy keeps going up, 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 up. Sometimes we might train it and the accuracy might go down a little. In fact, we see that a lot, especially with more advanced neural networks. We see error graphs that look like this basically, or accuracy graphs that look like that. But in general, the general tendency is that the accuracy goes up. And if we were to train this a little bit longer, I think we could probably reach like 94, 95% accuracy. So now let's visualize the results. Typically, we can't visualize the results. We've just wrote our own code to visualize these simple results. So in the first epoch, we can see that the neural network makes no distinction between cats and dogs. But further and further on, it sees more and more of a difference between them. So the fact that these images are being moved farther apart means that the neural network is seeing a difference, more of a difference. And right now, it's already pretty much classifying all of these training examples correctly that we have here. But if we had more examples, it would be classifying some of them incorrectly. We have another question. Which hardware would you suggest to train and run locally instead of in the cloud? It depends on the scale of your task, of your project. Like big companies would use supercomputers. Freelancer developers would use like some advanced kit of their own. Or it doesn't have to be advanced. It depends on the problem. You can buy a cheaper GPU, but that's not going to be satisfactory for every problem. NVIDIA GPUs, that's the one thing I can only really recommend that's going to be constant. You need a GPU and it should be an NVIDIA GPU because NVIDIA created their own, basically their own library that is used for Python to interface with the GPU basically. So this was an example of a classification problem. A classification problem is when we have some specific categories that we want to decide where it fits. Okay, we're running out of time, so I'm going to go a little bit faster now. We also have regression problems. Regression problems is when we're trying to predict specific values. It could be one value, like what the price of the stock market is tomorrow. It could be multiple values. Like if we were predicting the weather, we might want to predict what the humidity is going to be like, what the temperature is going to be like, wind velocity, and a bunch of other stuff. So right now we have an example of car prices. This is real data, by the way, that was taken from a car dealership. They have all sorts of different cars that they have different car manufacturers, models, mileages, KPP, fuel. Well, fuel is gas or diesel. I don't know why it says gas, like it's supposed to be gas. So body, KPP, I don't even know what that is. And once again, the amazing thing is that I don't have to, because the neural network will learn what these things are and how much they affect the final result on its own. So we want to predict how much that car is going to sell given all of these parameters. And we have like tens of thousands of examples. So when we train our model, at the start, it's not going to be very accurate. A loss of $15,000, so it's $15,000 off on average. But as we train it for more and more, we get better and better results. But eventually these results are going to asymptote. So this isn't to say that if we keep training this for years and years, we will get infinitely better results. No, eventually we will reach a plateau. So this plateau, it seems to be like probably around $3,000 it's going to plateau. And then we're going to visualize the result. So right now it's training for a while. 50 epochs might have been a bit too much. So it keeps giving us slightly better results. You can kind of already see that it's like asymptoting. It's not, okay, it kind of is like giving better results, but not really. Okay, so $3,266 off was our best. Also, if we look at this graph, we can see that at the beginning, there was no difference between the training loss and the testing loss. But as the neural network kept training, it started to perform a bit better on the examples that it's already seen. And it still performed better on the examples that it hasn't seen before, but there is some gap emerging that you can see here. So if we wanted to get even better results, we would probably need to either change the model, the architecture, or change the data. Right now, we are going to visualize how these prices look on a scatter plot. So in the very first epoch, we don't get to see epoch 1, unfortunately, but epoch 5, we are still off by quite a lot. But as we train for longer and longer, as the neural network keeps training, the prices between the predicted and the actual prices, they start to converge. So as we keep training, the result gets better and better. Now let's look at another example. We have a basic chatbot. So chatbots, by the way, this is another area where neural networks are used. Right now, we've been able to scrape together a fairly simple chatbot for this demonstration. The difficulty in creating any AI project, like 60–70% of the work is in the database. And the database that we've created so far, it's like mediocre, not going to lie. Chatbots in general, they aren't able to imitate humans perfectly right now, but as we give them more and more resources to work with, they would become better and better. So that's what we are going to see right now. Let's initialize the chatbot. So typically when we have chatbots, we usually train them on real data that people have said in some messengers. Like we might have these dialogue, these weird examples that someone posted in some forum or something like that. Now let's train on 1,000 dialogues. We have a data set of more than 11,000 dialogues. Let's only use 1,000 dialogues. So this is a small data set. We are artificially shrinking our data set to visualize the result. So after it's trained for 30 epochs, we are going to demonstrate the dialogues. So right away, we can see that the training error is decreasing, but the error on the test set is really lagging behind. Like in fact, this is a really gross example of overfitting. The neural network, it only tries to decrease the training error. A lot of the time it's going to do that at the expense of the test error. That's when we have the really bad overfitting that we want to avoid. So this is where the results, like we trained the neural network, but after we train it, the results are going to get worse and worse and worse. The neural network generalizes more and more poorly. There are ways to combat this, but we want to avoid this in general. So let's see what this looks like. Let's see some examples. You underestimate the situation. Now it's like talking about resolve or something. Like we have like some question that we're asking the neural network and the response is something that doesn't make sense. This is very bad. Now let's train it on 3,000 dialogues. So we are, once again, we're artificially shrinking our data set, but we are using a bigger data set than for the first example. We're shrinking it by less. So while this is training, I would be more than happy to answer any questions that anyone has. Or if you genuinely don't have any questions, then that's fine as well. But if you have any questions, then once again, please feel absolutely free to ask them. So 3,000 dialogues. Like we have a pet and we have like a vegetable. It sees the word joke here, but joke's on you and lied. Like it probably picked out the word joke a bit better, but still really bad. So now let's use our full data set. And while it's training, I will answer some questions. NK, thank you for the compliment, but if you're lost, what are you lost about? You can ask any questions and I will do my best to explain it. Is there any like specific topic that you want me to clarify a little bit more? Oh, you joined in a bit late. If you've, there should be, this should be recorded. I'm like 90% sure that this is going to be recorded and put up online. So you can catch up there if you want. So you're not a computer science, that's okay. So basically we have neural networks that perform all of this math that is going to train better and better. It's going to give us better and better results. So for 11,000 examples, we see that we don't have any of this gross overfitting. So the training data was still like, it performed better on the training data set than on the testing data set, but not by as much. All we really care about at the end is that this orange line decreases, that it doesn't increase. So now let's see the examples for 11,000 dialogues. What are some real things to talk about? Human nature, art, movies, food. So, okay, now it actually gives us something that makes sense. Like sometimes it's still off. Are you a bot? So what if I am? It's not giving us like good results. It doesn't resemble a human, but it's much, much better. And if we wanted to improve this even further, we would be tweaking the architecture. We would be giving even more examples. In our case, we can't because we don't have, we need to actually collect the database, which we didn't have time to do. But hypothetically, we could get even better results. But we can't, like, there is no way to make this resemble a human right now. Like, we haven't passed the Turing test. The Turing test is basically when a human won't be able to tell the difference between an AI speaking and a human speaking or typing some text. We haven't reached that point yet. Okay, so let's get back to the presentation and we have a few more questions. Used for the training. Oh, so we have two data sets. We have the training data set, which is basically we collect one big data set most of the time. We collect one big data set and we split it into two parts. The main part, like 80% of it usually is going to be used for training the neural network. It's going to be with the examples that the neural network sees, and it sees if the answers that it predicted are corresponding to the labels that we gave it. So the labels are when we actually tell the neural network that this example corresponds to this animal or this tree or something like that. And then we also have the test data set. The test data set is a smaller data set that's used to gauge how well the neural network has actually learned. It is being recorded. Oh, okay. Okay, so back to our main course. We have a long course that really goes through all of the ins and outs, like really comprehensively goes over every little thing that it goes over what we've just talked about. It goes over into the finer details that we've just talked about. But what we've just talked about is like not even 10% of the course. We go over like it's not even 5% of the course. We go over much more intricate things. We go over many detailed specific examples. So we have homeworks at the end of our courses, and we have people that will help you with those homeworks. So the point of those homeworks is to give like some practice, some examples to practice with, so it's not just all theory. So for any people who are looking to become any sort of AI developers, I know that a lot of people who are interested in machine learning want to inevitably become AI developers. We have a course that is going to essentially turn you into a junior AI developer. At the end of the course, we guarantee job placement. We have our own service, we have our own website, which is basically like a job hunting website where we upload your resume, we give you tips on how to better create your resume, and then we contact all of the firms that we know. Basically, we know a bunch of firms that take people that basically take people as employees, take our graduates as employees. This will be written out in the contract. We will have a contract if you choose to take our main course, and in that contract, it's going to be specified that job placement is guaranteed. It's only a matter of time. I want to say right away that so far, we haven't had a single student that hasn't been able to find a job. We offer support in every single step of the way. And it's only really a matter of time. Like usually takes a few months, but if you have some specific requirements, like you only want to work in this specific field for whatever reason in this specific company, then it might take a little bit longer. All you have to do, however, is show up for the interviews. So we will contact all of the big companies on your behalf, and they are going to be contacting you at the end. They are going to be booking interviews if you so choose, and all you have to do is show up. The salaries for junior AI developers, like entry-level wages in the United States, are between $45,000 and $85,000, roughly speaking. 45,000 is like small towns somewhere more sort of rural areas, well, small towns usually, and 85 is like New York, Silicon Valley. It depends on the exact company as well, but this is the general range. So we have two streams. Sergey, did you mention 300K is for the real big experts? 45K is what you expect to earn as a newbie in this field. 300K salaries is like you would need to have 10 years of experience. That is like, I'm not going to say that that's the absolute most, but that's like on the higher end. So it depends on how much experience you have for any job, right? Not just for AI development. For any job, your wage depends on your experience, what you can do, how much you can do, what kind of projects you can take on. 45 to 85K is the wage of a junior AI developer. That is just straight out of our courses, basically, or anywhere else. If maybe they're a self-taught developer, then it's just like the first job that you've ever found in this field, something like that. So we have two streams. The first stream is the light stream. That's the stream that most people take. That's the stream that basically people come to us from all sorts of different backgrounds. Like some people are straight out of high school or college or university. Some people are qualified doctors or mechanics or engineers, all sorts of people. I guess engineers do have some programming experience, but a lot of people like from the banking sector, people who don't have any prior coding experience. I would say that that's like 80% of our clients. There is absolutely no problem with that. Our main course, the Lightstream, teaches you everything that you need to know. All of the math, all of the, like we go over a little bit over Python, just the basics of how to code in Python. And then we just go over each of the libraries. But there are also sometimes people who have prior programming experience, be it in game development, be it in some other industry, that come to us, and they also want to pick up AI development. AI, by the way, is used in many different fields. It's used in gaming as well. It's going to be used like not just historically, like when you have your AI enemies, they would just be hard-coded simple algorithms, but it's possible to make AIs like that actually think like AIs. It's possible to make AIs that generate textures or environments for the game. So people who have that sort of programmer's mindset, if you have at least 1 year of prior programming experience, we recommend taking the Pro course. The Pro course covers the exact same material. It covers all of the exact same topics related with neural networks. But instead of going over the basics of Python and all of the frameworks that we're going to be using, you get to jump in straight into working with neural networks. So you'll graduate sooner. And a lot of middle AI devs, a lot of people who finish our Pro courses, they are able to skip that entry-level wage step, and they are able to jump in straight into like middle AI development. The wages for that are like between 65 and 125K, roughly speaking. Again, it depends on which job, where you're geographically located, and all of that other stuff. So sometimes we have people that come to our courses from another company. So we do two things. One thing is we create actual neural networks for some specific business, for some specific industry, or some specific organization, for some whatever the topic is. And sometimes the other thing that we do is we train people how to make their own neural networks so they can find their own jobs in the industry. Sometimes we do a little bit of both. Sometimes a company sends us their employee and they want to have a neural network as well. So that employee will be creating the neural network, but they would be doing that under our guidance. We would be helping them every single step of the way. We would be just from day one consulting how, like, which data you want to collect, what data you're going to be looking for, how you're going to want to collect that data set. You'll be testing out all sorts of architectures. At the end of our main course, there is going to be a thesis project. And once again, no one ever fails that thesis project. It's just a neat little project of your own creativity, sort of, that you can put on your own resume, that you can say that you made this really neat AI project, and we'll be helping you for as long as is necessary. For however much help you need, we'll be helping you every single step of the way to create that thesis project. So one more thing I briefly want to mention. There is, like, when people think of programming, there is like web development, game development. There is like people that work with raw databases. AI developers, they make a little bit more than all of those other developers, assuming the same skill level. Usually they make a little bit more because this is a really new topic, AI in general. It's a really new topic, and at least in the context of the scale that we're seeing it on now, and it's in really high demand. And as time goes on, the demand is going to increase. Like, the economy is catching up to the technology right now. So 100% the demand is going to increase. And it's also more interesting, in my opinion, because there is a little bit more creativity involved. So on to some more organizational topics. Our main courses start on the 26th of September. The Pro stream consists of 26 lectures, 26 unique lessons, so 26 different topics about neural networks. And the Light stream consists of 39 topics, so 6 months and 9 months respectively to finish those courses. We start with the very basic things in the Light course. In the Pro course, we skip straight into the neural networks. It takes about 10 hours per lesson to learn each specific lesson. There is homework at the end of that, so 10 hours is watching the lecture plus performing the homework. Then we will check the homework, and then we will give feedback. We will give an opportunity to fix any mistakes that you made so that you have the opportunity to learn. And it also involves, at the end, there is the thesis project. And what I want to really emphasize that there is a guarantee of job placement at the end of this. So we have our own team of TAs that checks homework, that gives you all sorts of feedback, gives you all sorts of advice that you need to do any project that you want. Right away, I want to mention that we are available 24/7. You can contact us in any way that you want. Like, there are a bunch of options, like you can text us on WhatsApp or on Skype or on Slack, or you can book like a video interview with us, not like an interview, but like a video chat. And we'll be able to help you with anything, like anything in the course. We'll be happy to discuss any theoretical subjects, any specific homework related topics. So we are available 24/7, and I'm not joking. For the entire duration of the course, 24/7 assistance. All of the learning is going to happen remotely. So all of the lectures are going to take place remotely. All of the checking the homework, giving feedback. We have a final exam at the end of the course, like an oral exam. That's going to take place remotely. Your thesis project, hunting for a job, is going to take place remotely. And if you want that job to be remote, or if you want to actually sit in the office, that's up to you, but I think most people would select remote. And at the end of that, we also hand out a diploma. Like, we hand out a physical certificate that shows that you finished our course. We can either like mail it to you by mailing address, or we can send a courier to you. So that's up to you. And obviously that is going to be remote. So let's talk about the pricing now. Both courses cost $3,490. That includes the whole, like all of the lectures for the 6 or the 9 months, depending on which stream you're taking. The guarantee of job placement is included at the end of that course. Once again, this will be specifically stated in the contract that you'll be signing. That comes with, so there are opportunities for internships. Right now, sadly, they're unpaid internships, but within like a few months, we'll be looking to make them paid internships. And that also comes with the physical certificate. So that comes with 24/7 TA assistance for the entire duration of the course. And if you want to switch streams, that's free. If for some reason, for example, you picked the pro stream, but it's a little bit overwhelming and you want to switch to the light stream, that's no problem. So we have a few questions that I'm going to answer now. I am a mathematician by hobby. I've tried learning to code in person, C++ and Unix, Python. I keep running into the same problem. The presentation and testing of items we have yet to cover. I end up having to Google the answer just to complete the given lesson so I can move forward. And I see the same responses. Stylistic thing in coding to challenge. Method person, I need to be shown exactly what to do before I can derive analogies based on a foundation approach. To me, approaching challenges through guesswork is guessing forward, and I am immediately turned off. I'm excellent in math and symbolic logic, not guessing. How does your style handle this issue? I think many people are exactly the same way. Like, we learn by actually doing the topic, by actually being shown specifically what to do. So we have lectures, online lectures. There will be live lectures. There will be, like, you can view them online at any time you want. You can view them again. And we also, like, if any topic is unclear, like if you didn't manage to ask the question during the live lecture, or if you opted to, which a lot of people do, it's absolutely fine, like view the rerun of the lecture, you can ask any of our AI developers. We have some really brilliant AI developers. Like, those guys are really brilliant. I'm not gonna lie, I don't know all of the tiny ins and outs. We have some brilliant people that, like, the previous clients we had are just like, they're really happy with those people that answer those questions. I've been taught by those people, and I can vouch from my own experience that some of the people that we have can really answer any questions that you have, discuss any theoretical topics in great detail. what is the expected dedication by lesson? 10 hours, that's the, well, not the expected dedication. It depends on the exact topic. It might take a little bit less for some, it might take a little bit more, but in average, we'll be looking at 10 hours. So we have one more question. Do you have profit sharing plans so I can promise you a portion of my future salary if you are sure that I will be employed? Any sort of questions like that, I would suggest talking to our sales managers. So I'm going to drop their contacts in the chat once again very quickly. I'm not sure if we do though, but we guarantee job placement for everyone. Like no salary sharing, nothing like that is necessary. We just guarantee it for everyone. It's only a matter of time. So you can contact our sales manager either by email, by phone, or on WhatsApp, or whichever you prefer. You can just head over to the website and then there is a chat box that pops up. 10 hours each lesson over how much time to learn the lesson. I'm sorry, I'm not sure if I understand the exact question. How many lessons? 26. Okay, so 26 lessons for the Pro stream, and the Light stream has 13 additional lessons on top of that. People who have who feel really confident, have a lot of programming experience, might want to just skip those 13 lessons, those first 13 lessons, and just delve straight into neural networks. So that's why we made the Pro stream. So moving on. For payments that take place before the 21st of August, we have 2 additional gift courses. We have the Introduction to AI course. This is just a very chill, sort of laid back course, no homework involved. There's just lectures. We talk about mostly the theoretical stuff, like how people go about collecting databases, what we might want to include in those databases, how the actual process of making the neural network and integrating it into some service looks like, and a lot of topics like that. So it's an interesting course, but it's laid back and it's just sort of a chill, nice course that you might want to watch while you're waiting for the main courses. Then we also have this course, the Basics of Python course. This course, Basics of Python, basically contains the first 7 lectures from our main course. And from my personal experience, I strongly recommend you to take a look at that. So I strongly recommend people to take that course, especially if you're thinking about heading on to the Pro stream. For people who want to take the Light stream, well, the advantage of taking that course might be that you have a little bit more experience, that you have a little bit of a head start. But for people who have, even if you know Python, when I first took these courses, I was pretty confident with Python. I even used some of these specific libraries that we'll be using in the main course. I had some experience with them, but we go much deeper into that. So we cover all of the libraries like NumPy, Pandas, Matplotlib. We cover them in great detail. We cover all of the theory. And if you want to skip the first 13 lectures, the first 7 lectures really contain everything you need to know, especially regarding the libraries, because there are a lot of people who know Python, who feel confident with just the Python. But we also have these small niche moments, like these small niche libraries that if you know all of the ins and outs of these libraries, the difference in the main course will be between thinking for 5 hours how to do this one problem, how to maybe reorganize your data in this one fashion, looking for all of the functions, Googling the whole problem many, many times, versus spending 30 seconds just Googling the syntax, knowing that this library contains all of this information and all you want to know is the syntax. I've run into countless of these instances. And that concludes our presentation for today. So everyone, thank you so much for listening. Thank you so much for watching this. And I hope to see everyone in the main course. So right now I will spend a few minutes answering any more questions that you might have. So if you have any questions, please feel free to ask them. 10 hours each. Okay, so 10 hours over a week, 10 hours over a week. And once again, this is a very, an estimate, plus, minus. And also, it's not there isn't the specific requirement of 10 hours. we just give you the material to learn from, and we offer help in learning, right? But some problems on the homework might be optional. For example, if you want to learn the given material to a higher level, you might want to spend more time on this specific homework. And by the way, there are no set due dates, so you can also like go back to a homework that you started 3 months ago. Like there are set due dates, but they're not like really, really hard due dates. You can hand in your first version of the homework and then go back and redo it, or you can just hand it in much later, and I think you'll get deducted like a tiny negligible percentage of marks, which doesn't really mean anything. So effectively, there are no like firm due dates. So you might even want to like make your own problem that you want to solve after you've seen like all of the material. You might want to try out your own stuff that the homework isn't telling you to do, but you might want to do that on your own. I've had a lot of those moments. So once again, I'm going to drop our contacts. That's the contacts of our sales department, our sales manager. And yeah, if anyone has any other questions, I would be absolutely happy to answer all of them. So I think that concludes our presentation for today. I hope that everyone enjoyed it. You don't see the contacts. Ouch. That's happened one time before. Let me paste them onto the screen. So let me just quickly paste them onto the screen. Yeah, if you want to take a screenshot, no problem. Let me actually make them a bit bigger. Let me see if okay, yes, this is how, no. I don't know how to make them bigger. So yeah, I hope to see everyone in the main course. Take care, guys. Have a wonderful rest of the day. Thank you. Take care.